ahead and filled in the rest of the table. You can do the same for the bottom one, and it's also on page 105 of your book if you are having trouble filling the rest in. The positive predictive value for the specificity of 70% is the number of people that tested positive, the percentage of those that are actually sick. So it's 1,000 over 3,700, which is about 27%. If you do look in your book on page 105, or if you fill in the table based on the specificities, you'll see that as the specificity goes up to 95%, the predictive value also goes up to 69%. So if you varied the sensitivity, you would see that as the sensitivity decreases, there's less true positives, less people in the sick and tested positive box, which is going to decrease that numerator of the positive predictive value, and then we'll decrease the positive predictive value overall. So go ahead and fill in the rest of that table and just play with the numbers to think about what determines positive and negative predictive values, and what impacts changing the sensitivity and specificity, even prevalence, will have on those different values. Another source of variability within tests is the test reliability and repeatability. So if you give the same test to the same person, does it vary within the same subject, which would be intra-subject variability. Or if you have one person diagnose many different people, are there different results between readings? So if I'm reading a chest x-ray for tuberculosis as an evaluator, sometimes there's some inherent variability in the way I read things, whether I say that it is a case of tuberculosis or not, and that would be intra-observer variation. And then the final type is the inter-observer, and that is between observers. If we look at the same x-ray, the difference between us saying that there is a disease or not. So that's another element of reproducibility or repeatability of a test result. And then another measure of accuracy is the percent agreement between observers. So if we do have more than one observer, there is a certain amount of time when they are going to, by chance, say the same thing. So if we give them a bunch of x-rays that don't have any particular pattern to them or disease, just by chance they're going to pick the same value a certain amount of times. Whereas they also have a trained eye, and they will have an observed value. So the percentage agreement between observers is the amount of time that they agree divided by the amount of times that they read something. And then another element of that is the kappa statistic, which is the percentage. It is a measure of to what extent do different observers reading the same test agree beyond what we would expect them to by chance alone. The kappa statistic looks at how much more percent agreement there is between observers, so how much more inter-observer variation there is as opposed to what we expect randomly in the numerator. And the amount that could be improved for percent agreement from randomly using those observers in the denominator. So it's a measure of perfect agreement would be 1 minus that randomly observed. So how much do we increase or decrease the perfect agreement by using random associations between observers? The kappa values range from 0 to 1, 0 being very poor agreement. So that would be, in that case, the percent of times the observations that were made at random were in agreement would far outweigh the percent agreement that our trained and observed observers were making the correct call. If it's 1, that means perfect agreement the entire time. So that would be the percent observed would equal 1 over minus 0 over 1. Anywhere in between that, the closer it gets to 1, the better it is. If it's closer to 0, it's a worse agreement. So ideally, you want to have a high kappa value close to 1. This is a way to look at whether the tests are valid and reliable, or just reliable. So if a test is valid, if we look at the bottom, the difference between reliability and validity. So validity, of course, is actually getting the right value, whereas reliability is getting consistent values across a lot of different tests. If your tests are valid but not very reliable, you are casting a wide net. So you're catching all of the cases, but you're having a lot of false identifications. And that would be like that second bullseye. We're putting a large distribution around that bullseye. So we're including a lot of cases that maybe we shouldn't have. Or there's a test that's reliable but not valid, which has a really tiny skinny distribution if you're thinking of a normal looking distribution. Or in that case, a tight group is in that first bullseye. If that has reliability, all of the cases are all within that same diagnosis. That means every observer is doing the same diagnosis, but the diagnosis is wrong, so it's not a valid test. Overall, you want something that is both reliable and valid. So you want something that is a very tight distribution that is around the true value, so that you want to be able to consistently identify the correct cases. Here is, if you look at, here's reading 1 and here's reading 2. So again, this is if the observers are looking at chest x-rays. Reading 1 is going to go through each of the x-rays and say whether they're abnormal, suspect, doubtful, or normal. And then reader 2 is going to take those same x-rays and look at abnormal, determine if they're abnormal, suspect, doubtful, or normal. And the percent agreement is every instance where they had the same reading for the same x-ray, same subject or patient, over the total times 100. The kappa statistic, in this case, would just compare the same data to an expected data based on a normal amount of error associated with a randomly distributed observations. So it's sort of like the chi-squared test statistic, where we look at an observed and seeing if the observed is very different from what we would expect randomly by chance. And if that is, again, if it's close to 1, then those are weighted more towards the agreement that is from the observation. And that is kappa statistic that is 1 is very good, whereas 0 would indicate that they could be doing it at random and it would still get the same amount of agreement between observers. Okay, and the final thing I want to talk about tonight is the cluster analysis. And cluster analysis is any group or series of events, diseases that are, some sort of health-related phenomena that's in a well-defined distribution pattern. So if you look at the little picture below, those are all different distributions, clusters around some sort of place or time. Clusters can be in time. So for example, we talked about Legionella last week. That was a specific case of time. A cluster of people came down with that particular disease in an afternoon. So that's distributed by time. They could be by place. So the particular locations of the Ebola outbreak is different places. We're monitoring that as a cluster. Or it could be in a person. So if breast cancer, if you have the BRCA gene, you have a elevated risk of getting breast cancer. In that case, there might be a cluster within a family because it is genetically connected. Or it could be a combination of these. So a lot of the health disparities we've been talking about this term fall within not only place, location, but also demographic lines too. So that would be person characteristics. We looked at this, the HIV/AIDS cluster. We saw this in the band played on video, and this was the cluster with Gaetan Dugas in the center. He was the index case, and each of these people that he had sexual contact with then went out to have their own clusters. So this showed that it was a sexually transmitted disease. Okay, so here are 4 exercise questions. I would like you to do these and post them to D2L by next class, and then I can give you your participation points. I will post the answers to them tonight as well, so if you're having any trouble, you can of course look on them, but as always, I don't grade them. I just want to get an idea of where you're at, so please, don't just copy down the answers that I put up there. You can scan it. If you just do it handwritten, you can just scan it and post it up there. And if you're having a lot of trouble posting stuff or scanning stuff or whatever, you can just give it to me next week as well. But I do want to make sure you get it done before the midterm. Okay, so let me just review really quickly what's going to be on the midterm. I want you to know what is epidemiology, what's the sort of thread throughout all of the lectures. I want you to know what defines an epidemic. I want you to know briefly about some of the important people and the different innovations, just the main guys and gals that contributed to epidemiology, different ideas about the modes of causation. Obviously, I want you to know the difference between prevalence and incidence. I want you to be able to calculate either or both of those. I want you to be able to identify the epidemiologic transitions. I want you to know sort of generally each of the transitions, prehistoric, first, second, third, what types of diseases, why those types of diseases were more prevalent, and things that changed from one transition to the next. Rates, I want you to, so for that epidemiologic transitions, just review that article from Harper, I believe it was. The rate, I want you to know about rates, person time. You should be able to convert different units within rates. I want you to know what to do with incident rate calculations. So if I give you a study population with different inclusion and dropout and censoring dates, I want you to be able to calculate person time and then the incidence based on that. All those risk calculations that we talked about last week, I believe. So relative risk, hazard ratio, odds ratio, percent attributable risk, efficacy. As always, I want you to know how to calculate them, but as well, I want you to be able to describe what they mean and be able to interpret the results of it. Then I want you to talk about the elements of disease transmission from epidemiological triad, the factors of disease spread, all that stuff we talked about with the plague game. And then the steps of the outbreak investigation. This is pretty general. If you have any questions, as I said, please feel free to email me. And we can, anything you guys ask me, I'll post on the discussion, anonymously post on discussion, so you guys can share information and questions. But the midterm will be next week. It will be a combination of short answer, calculations, fill in the blank, etc. So that is coming up, and it is a significant portion of your grade, so prepare for it. And let me know if you have any questions. Thanks, and sorry again for the inconvenience of the snow day. Have a good week.